Well, if you're checking out these videos in some kind of sequential order, you may just have watched recently a solubility curve analysis video, thinking about how the temperature of a solvent plays an important role in how much solute it can dissolve. Almost all solid salts, as solutes, dissolve better in warm water than cold water. And maybe that makes sense, doesn't it? On a molecular level, on an atomic level, on a cartoon level, where you imagine these particles moving faster as they're getting warmer, and the solute particles of water moving faster collide with each other more frequently, also collide with each other with the solute particles more frequently, and in a sense are dissociating or breaking up those ionic bonds between the potassium and the chlorine or chloride and the potassium and the nitrate, or the lead and the nitrate, or the potassium and chlorate, etc. The water bounces into them more often with more force, and so it can dissolve more of that salt in a given volume of solvent. But you know what? That same reasoning doesn't hold, it turns out, for gases dissolved in water. Why would it not work for gases dissolved in water? Why would it be backwards for gases dissolved in water? Why would warm water be able to dissolve less gas than cold water? Well, I have some experience with this when I was a kid anyway. As soda pop. Doesn't cold soda pop hold its fizz better than warm soda pop? And why is that? When you open a bottle of warm soda, doesn't it bubble a lot more than the cold soda? Interesting. Think about it on a molecular level. Why would it be that cold water can dissolve more gas than warm water? Do you want me to answer the question? I suppose you do, because you're watching, you're listening. Sorry. The answer is, again, collisions. If I'm thinking about a particle of gas, carbon dioxide in the red here, as being able to dissolve in the water, in a sense, the CO2 being nonpolar, it actually might matter if it's polar or nonpolar, but many gases are similar. The particles, the molecules of gas are able to somehow squeeze in between or amongst the water molecules. And if the water molecules start moving faster and faster, they collide with each other more frequently. They also collide with the particles of gas, the molecules of gas. Although it's hard to imagine those molecules are collected together and could think about them or see them as gas, but maybe you could on a small scale. But as the water bounces into them more frequently, it kind of pushes them out of solution, and it pushes them, collides with them, and I guess I like to think about it as pushing them out of solution, pushing them together. So as it works for nitrogen gas, oxygen gas, as the water gets warmer from 0 degrees to 100, from freezing to boiling, as I boil the water, almost no oxygen or no nitrogen gas will stay dissolved in the water, and probably at least at the very beginning of the boiling cycle, all the remaining dissolved gas gets pushed out of the water. Well, that has a name. It's called Henry's Law. Let's get to that in a second as well. Another important factor in terms of gas solubility is the pressure of that gas, or the partial pressure of that gas. Think back to the chapter on gases in last first semester general chemistry. If I push harder on the top of that solvent with increasing the pressure of that gas above the surface of the water, in this case water, does it make sense to say that more of the gas is pushed into solution? So here I have some kind of funky equilibrium between CO2 in the water and CO2 gas above the liquid, above the solution, equilibrium, a balanced mixture. But if I were to push harder on the plunger, decreasing the volume, increasing the total pressure and also increasing the partial pressure of CO2 above the solution, in a sense I force more rapid collisions. Not in a sense, I absolutely do. I imagine this anyway. I increase the collisions of the gas molecules in the airspace with the solution, surface of the solution. And in a sense, I really do force them more frequently to go into solution at the surface. And eventually they'll reach a new equilibrium if I were just to hold that right there. Excuse me. But I would for sure have more carbon dioxide forced into the solution. Isn't this why Coke and Pepsi and etc., all the sodas that have fizziness are bottled under pressure? When you first open the bottle or the can, it goes ksh. That's some of it trying to escape. In other words, there's a little layer of pressure, or a little layer of gas above the liquid, and it's pressurized. It's under a greater than 1 atmosphere of pressure. I don't know exactly what it is. Probably maybe 2 atmospheres of pressure. Interesting. Solubility of gases. What's this talking about? Oh, partial pressures, yeah. So, interestingly, the partial pressure of oxygen increasing doesn't affect the solubility as much as carbon dioxide. Carbon dioxide solubility increases pretty much linearly with increased pressure. But, as I was saying, there's a name for that. It's called Henry's Law. There's my can of soda pop. And just bottled under pressure so that when you crack the top it goes whoosh, and gas escapes, or the pressurized gas above escapes, and then quickly, because of that reduction in pressure, the carbon dioxide begins to come out of solution, and you see all kinds of bubbles. Especially if you were to pour it into a glass, you'd see the bubbles coming out of solution, the bubbles of carbon dioxide escaping, forming out of solution, escaping from the solution. So the temperature deal is right here, wrapped up in the constant, called the Henry's Law constant. So we could talk, I'm not going to, but we could talk about how the constant K is intimately connected with the temperature. But let's not ask that question anymore. Let's ask the question, because that may not actually be a linear relationship. But the pressure of the gas, the partial pressure of the gas above the solution is directly and linearly related to the concentration of that gas in solution. It's called Henry's Law. So it looks like we're talking molar concentration. We have a molar Henry's Law constant in molarity per atmosphere. So if I had 1 atmosphere of pressure, partial pressure of oxygen above the solution, and then jack that pressure up to 2 atmospheres, that would basically double the amount of gas, oxygen gas, that dissolves in the water. This little question talks about 80 liters. 80 liters? Does it matter? It says, calculate the mass of nitrogen gas. Oh yeah, that would matter. The 80 liters, that's a lot of volume. In a fish tank, partial pressure of nitrogen is 0.78 atmospheres. So it's like a fish tank open to the air. And the part of the air that is nitrogen is 78% by volume and by particle nitrogen. So indeed, the partial pressure is 0.78 atmospheres, and the constant, according to this table, at room temperature for nitrogen, 0.00061 molarity per atmosphere. So the atmospheres cancel, and I'm left with a molar concentration of nitrogen in the fish tank. If I had 80 liters, how much nitrogen would then be dissolved in that 80 liter fish tank water? And it comes out to 1 gram-ish. Good thing the fish don't breathe nitrogen, they breathe oxygen, but you could do a similar calculation. How would this change if you're talking oxygen? Well, that constant would change, wouldn't it? So that constant would be, instead of 61 milli whatever, it would be 1.3 millimolar per atmosphere. Anyway, so it's 60 times bigger-ish for nitrogen than oxygen. I wonder why nitrogen's more soluble in water than oxygen. I'll let you mull that one over. In any case, the partial pressure would change also, because our air is only 20-ish% oxygen. So this would be 20%, or I'm sorry, 0.2 atmospheres, and this would be 0.000. No, my bad, I lied. Oxygen is more soluble than nitrogen. Oh my goodness. So this is, yeah, that would be 0.6 millimolar per atmosphere. This is 1.3 millimolar. So, okay, oxygen is 2 times more soluble in the water than the nitrogen is. So, anyways, or you could look at this relationship of concentration versus pressure and graphically, and if it's a linear relationship, then actually the slope of this line gives me the Henry's law constant, K sub alpha, if alpha is we're trying to describe the gas that we're dissolving. So the slope looked like rise over run. Sure is curious and interesting and amazing how we can use mathematics to describe some of these physical and chemical properties and connections we always look at. Another one, if we like. How many grams of NH3 will dissolve in 1/10 of a liter solution? Partial pressure 7.8 torr. That's quite a bit, huh? 7.8 torr. And the constant's given to me. And 1 atmosphere, they're reminding me is, oh no, 7.8 torr. That's nothing. But still, ammonia is a nasty gas, so maybe we don't want to jack the pressure up too much and come in contact. Take the risk of coming in contact with too much ammonia. Okay, so 7.6 torr. That's like, what's that? 1/100th of an atmosphere. So yeah, what would the concentration know? How many grams of NH3 will dissolve? Well, first we might have to find the concentration and then work from there. Feel free to pause the video and try it yourself if you'd like. Or if you don't like, then here's the answer. So I took the Henry's law constant. Did they mention that? Wow, 58 molar per atmosphere. Ammonia is amazingly soluble in water. It goes back to like dissolves like. Why would NH3 dissolve so well in H2O? They're both polar. There's hydrogen bonding going on there, isn't there, between the nitrogen lone pairs and the hydrogens, etc. So anyway, 58 molar per atmosphere, and 7.6 torr is only, what would we say, 1/100th of an atmosphere? So 1/100th of 58 is 0.58. So 0.58 molar, that's the stuff you buy from the grocery store as ammonia water is more concentrated than that, a little bit. In any case, in 1/10 of a liter, then, 1/10 of a liter times that molar concentration in moles per liter, the liters cancel, leaves me with 58 millimoles. Have you guys thought about milli? What a milli is, a thousandth, so 58 thousandths of a mole. And then I can change the moles into grams. So even though the constant is large, the partial pressure of NH3 above that solution was pretty low, and the concentration therefore is also pretty low. Whew, are you asleep yet? I'm almost sleeping. I need a nap. No, I'm kidding. But thanks for coming in to watch, and I'll see you in class.